Video we're going to continue our discussion of compound growth, but specifically with, say, like monetary accounts or money, okay, but compounding interest and growth. And so in an effort to continue the conversation, we'll pick up where we left off, which was necessarily we would come up with a formula that gives us the amount A and say as a balance in a bank account for the sake of convenience here at any given time, so long as we knew the initial amount or the principal. Okay, we also knew that n, okay, n represented the number of compoundings per year. That is, if it was quarterly, it compounds 4 times a year. If it's monthly, it compounds 12 times a year. Semi-annually, twice a year. Biannually would be only a half a time per year because that's once every 2 years. If we talk about in an annual instance, we said R represented our rate, okay, and T represented our time, always in years. Okay, T is always in years. But what I'd like to do is in this video pose the question, what if we had something that didn't compound annually or semi-annually or monthly or maybe even like semi-monthly, which would be 24 times a year, or maybe daily, that'd be like 365.248 times a year, but something that compounded so many times that you couldn't even tell that it was never compounding. That is, you can tell that it is always compounding, something that we'll say compounds continuously. So you hear in math a lot of the time we talk about continuously compounding interest. And so the best way to kind of get into that is maybe we start to look at, okay, so what if we were to say, now, let's take our original formula, but we'll say n approach a sufficiently large number, almost like infinity, increase without bound. What would this necessarily cause to happen? So the first thing I'm going to do is I'm going to build in a side clause here. We're going to let m, this quantity m, okay, equal n over r. And without arguing too much about why, I'm just going to say let's let that be for now, okay? And maybe we'll confront that in another video. But that being what it is now, we say, okay, so if that's the case, m is n over r. What I'd like to do is solve for n, and then we'll take what we get there, we'll substitute it back in for every instance of n in our original formula. So solving for n here, we say, okay, so take both sides times r, of course, and those would cancel. So we say it follows that n equals m r. So using this definition of n, let's take a look at our formula here for amount in a bank account again. We say that'd be p plus 1 plus, excuse me, n is, I've got something backwards here that's kind of embarrassing. We say this is r over n, of course, r over n. But we say this would be r over n, and n we know is mr. R. This is all to the nt, but of course we know n is the same thing as mr and t. And I love this example because it spells Mr. T. But anyways, that's neither here nor there. What we're essentially saying is now we can simplify this a bit. So we've got p times quantity 1 plus really just 1 over m because of the fact that these r's drop out here. We say this is now to the MRT, and I'm just going to write MRT. I'm going to do a little manipulation here, a little algebra. We say P 1 plus 1 over M, and I'm going to assign this value M as being this exponent here. I'm going to put brackets around this. Yes, I am. Okay, and this is all to the RT. But of course this holds true because we've got now a power or an exponent to another exponent, which would mean we would just multiply them anyways and end up with MRT. But the reason why I kind of bring that M down here is because we say now, if we were to take the limit of this as M approaches infinity, that is, if we let M get very, very large, this is something that we explored in one of our previous videos. This is actually the natural log base as M gets sufficiently large. So we could say continuously compounded interest, we would say A, the amount, is equal to P with a base of E, and then E is being taken to that leftover exponent RT. So we say, all right, let's put this one in our back pocket here. We say n compoundings annually is given by the formula A equals P 1 plus r over n to the nt, whereas continuous compounding. Continuous compounding is, and I'll even write annually, okay? So annually, I don't think I wrote it very well last time. Annually, is given by the formula the amount I have is equal to the principal times base of e to the RT. And so we say, just forget n. As n got so large, this collapsed down to e anyways. And yeah, as a matter of fact, between these two formulas, you know, you're supposed to be remembering both of them. But man, continuous compounding is actually really simple to remember, and it's actually really easy to use. Let's run a real quick example on this. How about we say, all right, so we're going to drop our money in a bank account. This is fictional. This would not happen, but it's convenient. We say, all right, so our initial amount, for the sake of convenience, we'll say is $1,000. Thousand's a good number to work with. We say, all right, and they're going to give us a rate of, you know, 3.1%, and this is for a time of 3 years. And this is compounded continuously. So we say n is almost, it's in infinitely many large, okay? So we say, given these parameters, how much money would we have after, say, our 3-year period? We say the amount here, okay, was our principal, P, just bringing down our P, times e to the now RT. Of course, T is 3 years, but I want you to notice again, okay, like in the last video, we say 3.1% needs to be converted to a decimal. So that would be 0.031 after bumping that decimal twice to the left, and that is times 3 years. So now I'm simply just going to pull out a calculator, which is what we would necessarily do. We can clear this out. We say, okay, so we had an initial investment of 1,000, and that is now times e to the power of point, and that was 0.031, and that was times 3 years. And we simply say, okay, thank you, calculator, 1097.46. So we say after 3 years, we should have an amount that is 1097, I think it was 36. I'm going to write ish because I rounded it to the nearest penny. But yeah, that's just a really simple example of how we might utilize continuously compounding interest. So if you're going to bring anything away from this video, is really that this formula exists, and whenever you work on compounding interest problems, just know that whenever it's for a certain number of compoundings per year, that is quarterly, semi-annually, biannually, whatever, you need to use this formula. You have to have n in there. But when it's continuous, it's like, great, we'll just use a equals p e to the RT. It's really, it's easy, so enjoy.